These problems will correspond with the notes for 7-8. On 7-8, you'll be either using the exponential growth or exponential decay formulas. This will be the one you use for exponential growth. This will be the one you use for exponential decay. The only difference is that it'll be a negative on the exponent. So half-life of sodium-22 is 2.6 years. So determine the value of K and the equation of decay for sodium-22. So A would be the initial amount of the substance, and Y, based on this formula, A is going to be how much you start with, T is how long in years, K is going to be the constant, which is going to represent the growth, or in this case, the decay. So the amount we start with, E is our natural number, K again is the constant, T is how long, and we're going to find out how much would be left at the end. So the initial amount will decrease, and we'll find the final amount using this formula. Here, the initial amount is A, it'll increase and grow, and then we'll find the final amount through that formula. So if we set up the formula, and 2.6 is going to be our time in years, so after 2.6 years, there should be half of the amount we had in the beginning, because that's its half-life. And that's what that means, is if it's its half-life, then the amount is going to be half as much after this many years. So here's our formula for decay. So we would put in A is the original amount, and then it's going to end up being half of A at the end. And the rest of the formula is A, E to the negative K. We don't know what K is, but after 2.6 years, then the original amount will be half as much at the end of 2.6 years that we started with. So if we divide off the A from both sides, divide by A, then we get 0.5 equals E to the negative 2.6K. If we take the natural log of both sides, then the natural log E of negative 2.6K, the natural log of E cancels. So we just get negative 2.6K is equal to the natural log of 0.5. Divide both sides by negative 2.6. And so you put this amount in your calculator, and we get approximately 0.2666. So that means that K, our constant, is 0.2666. So the equation for the decay of sodium-22 would be Y, which is the final amount, would be equal to A, the initial amount, times E to the negative 0.2666T, where T is the amount of time in years. So if we set up this one, radioactive iodine is 8 hours. What is the value of K for radioactive iodine? Even though the formula is set up for, and the formula says T is the time in years, in this case we can use 8, we can use hours, we can change it to hours. And so when you set up the 0.5, the 0.5a equals a times e to the negative k to the 8, then basically you can just divide the natural log of 0.5 by 8 and get, and it'll be actually a negative 8, and you can get a 0.8664. That's not on your paper. But that's what the answer would be for this problem. It would be the positive 0.866. So if you use the K of 0.866 negative, or positive 0.0866, if you use that amount for K in the decay formula, then you want to know 20%, so you could say 0.2a equals a times e to the negative 0.0866, and then you'd need to solve for t in time, and you should get 18.58 hours. Time in this case would be in hours. Now in this situation we have growth, so we'd use the growth formula. Here's the growth formula. And we put 1.32 as the value, or the population at the end, which was 2007. In the year 2000, it started out as 1.26 billion. We'll just use 1.26. So 1.32 billion at the end, 1.26 billion at the beginning, and this was over a period of 7 years. So we need to solve for a value of k. Divide both sides by 1.26. Take the natural log of both sides. That'll make the natural log of e cancel, and you'll just leave left with 7k equal to this amount, which you can put in your calculator. Divide that amount by k, or by 7, and you get the value of k. Plug all that in your calculator. Natural log of 1.32 divided by 1.26, and then all of that will be divided by 7. .0066. That's our constant. So their growth is about 0.0066, and that means it's about 60 or 0.66%. When will the population reach 1.5 billion? Well, you use your 0.0066 for k, and we want to know, we're going to solve for t in this situation, the time. The end value is 1.5. It starts out at 1.26, and then we plug, take the natural log of both sides. Natural log of 1.5 is 1.1905. Natural log of 1.5. Hold on. I skipped a step. We need to divide both sides by 1.26. So 1.5 divided by 1.26 is approximately 1.1905. Then we need to take the natural log of both sides. and then the natural log of E will cancel, and we'll get the 0.0066 t is equal to the natural log of 1.1905. Divide both sides by 0.0066. Put that in our calculator. Good. 26.42, which is our t, which is our time. So that means the population will reach 1.5 billion approximately in the year 2026. We started out at year 2000. 26 years later, 26 is our time. India, on the other hand, their population is growing also. In 2007, China had 1.32 billion, and in 2007, India had 1.13 billion. So how long will it take before India's population passes up China's? Because India is growing at a rate of about 1.5%, move the decimal over twice, when China was only growing at 0.66%. So if India is growing faster than China, then at some point they will pass it up. They will pass China up in population. So the 1.32, which represents China's growth, will be less than India's growth at a certain time. So we take the natural log of both sides. And since it's multiplication, we can break it up into two different double logs. The natural log of E cancels, and we're just left with 0.0066t. Same thing over here, natural log of E cancels, and we bring down the exponent, 0.015t. Subtract off the natural logs, subtract 0.0066t from the 0.015t, and then we divide both sides by 0.0084. Put that in our calculator, and that comes out to about 18.5, which means that in 18.5 years, India will pass up China. And if it started out in 2007 and you add 18.5, you get about the year 2025 as the time when it will pass China. The logistic growth function is a little bit more complicated. A, B, and C are positive constants. B has to be positive, or actually less than 1. Logistic growth function, here it is. T is still time. So if a city's population in millions is modeled by this formula, and T is the number of years, you don't have to understand where the formula came from. You just, if you're given this formula and T is the number of years, we want to graph that function. That's the number of years since 2000. We're going to graph that function. It looks something like this. Just put it in y equals, and you can see the curve. And it starts out, and then it sharply levels off. The question I have on your paper is, when will the city's population reach 1 million? So if you look at the graph, it indicates the population will reach 1 million at around 3. You replace f of t with 1 and solve for t in the equation. You could do it that way also and yield 2.78. I would suggest using your calculator and estimating based on the graph. As we go to the homework, looking at number 1, when it's the fishing problem in an overfished area, if the catch of a certain fish decreases exponentially, we use the decay formula. It says K is going to be 0.084, and we're going to figure out how long it will take for the catch to be half of what it currently is. So we'll set up where we want to know when it's going to be half the current amount. Current amount is going to be A, e to the negative 0.084 t. T is our time. So we divide off the A on both sides. That'll always cancel. And if you take the natural log of both sides, so the natural log of 0.5 would be equal to the natural log of e to the negative 0.084 t. Now the natural log of e will cancel. So basically, you're left with just negative 0.084 t. That will be equal to the natural log of the 0.5. So if you want the time, you just divide both sides by negative 0.084. Put this in your calculator, natural log of 0.5 divided by negative 0.084, and you get a time of approximately 8.25 years. Number 2, population on a census is going to be growing. Now, this is basically our growth formula. And we want to know if the population, what the population is going to be after 30 years. So P is going to be the population after 30 years. Currently it's 3.5 million. Following that formula, it would be E to the rate would be 1.5%, which would be 0.015. So that's going to be our exponent, 0.015, and then times 30 years, and we're trying to figure out what the population will be. So if we put this amount in our calculator, 3.5 times E to the 0.015 times 30, and you can put that, you need to make sure that you put all this in parentheses to make sure the calculator does it right, and you should get a population of about 5.489, which is about 5.5, and that would be million. I think million, yeah, million. Number 3, population in thousands is modeled by this formula right here. T is years. How many years will the population of the city be? 120,000. So we don't want to put 120,000 because P is in thousands. So this represents 80,000 in the beginning. So we want to know 120,000 will be the end result. If it starts out at 80,000, to the 0.015 t, and we're trying to solve for t. So we can divide both sides by 80. And that becomes 1.5. So we have 1.5 equal to e to the 0.015 t. We take the natural log of both sides. We'll get the natural log of 1.5 equal to natural log of e to the 0.015 t. The natural log of e will cancel, and you're just left with 0.015 t. Divide both sides by 0.015. Put this in your calculator, and you'll get a time. The time should come out to be natural log of 1.5 divided by 0.015. You get 27, so approximately 27 years. Number 4, bacteria. How many days will it take for a culture of bacteria to grow from 2,000 to 50,000 if K is going to be 0.675? So if it starts out at, and we'll go in thousands, so if it starts out at 30,000, or it ends at 30,000, and it starts out at 2,000, e to the 0.657 time. If we divide both sides by 2, we get 15 equals e to the 0.657 t. Take the natural log of both sides. E will cancel, so you'll be left with natural log of 15 equal to 0.657 t. Divide by 0.657. And we'll get a time of natural log of 15 divided by 0.657. Natural log of 15 divided by 0.657. We'll get about 4.1218. So approximately 4 years. Uh-oh, that was a 5. Back up. That's a 50. So this should have been a 50. Changes that to 25. Changes that to 25. So let's back up. Natural log of 25 over 0.657. Natural log of 25 divided by 0.657. That's better. 4.899 or 4.9, close enough to 5 to just call it 5. 5 days, or 4.9 days. Let's go to number 5. Nuclear reactors produce and use the plutonium-239. If the half-life of plutonium-239 is 24,360 years, what's the value of K? So if the amount we start with, A, if we want to end up with half of that amount, and we want to use E, we're going to have negative K, we're going to solve for k, and we know that the half-life number is 24,360 years. Then the a's, when you divide by a on both sides, the a's cancel. Take the natural log of both sides, you'll get the natural log of a half, or 0.5, is equal to the natural log of e to the whatever. The e will cancel, and you'll just be left with negative k times 24,360. We'll divide both sides by negatives and 24,360. So in your calculator, you would have the natural log of 0.5, do it like that, mess with fractions, divided by a negative 24,360 would give you the k, the constant for the half-life. Put that in your calculator, you get approximately 0.000285. It says 2.85 times 10 to the negative fifth. That would be your answer. Depreciation. Global positioning satellites use satellite information to locate the ground position. The survey firm bought GPS system for $12,500. The GPS system is now worth $8,600. How long ago did Abu buy the GPS system? If the K that we're going to use is 0.062. So if it's now worth 8,600 and it was worth 12,500, and we want to find the time, and K is 0.062. This is a decay formula because it's decreasing in value. 0.062 t. We're going to solve for t. So we're going to divide both sides by 12,500. Then we're going to take the natural log of both sides. That'll cancel the e. And then we're going to divide by a negative 0.062. So take this amount and divide by negative 0.062, and you should get the value of t, which I ended up with 6.0317, so it's approximately 6 years ago. On logistic growth problem, what is the maximum population of the habitat? The top number is going to be your maximum population. If you put this into y equals and you start going down the x table, the numbers will get bigger and bigger and bigger, and they'll start to get closer and closer to 105,000 without reaching it. And then if you scroll through your table, let's just do it. So my calculator in y equals, if I put that whole thing, and you got to put it in the calculator right, 105,000 divided by 1 plus 2.7 e, and as the exponent I need to put that in parentheses 2, 0.09 negative 0.0981 t, or we're going to call it x, close parenthesis. And when you go to the table and you see the numbers started out at 0, or even small, or even a little bit bigger, you would see the numbers start to grow as the x values get bigger. The y values are growing. They're growing, and then when you go back up a little bit, it reaches 101 or 100,000 at approximately somewhere between 40 and 41 years. Remember, t is x, and t is time. So the x values are the years. So it reaches 40, or it reaches 100,000 at about 40 to 41 years. And I'll show you, as we keep getting bigger and bigger in years, it'll get closer and closer to 105,000. But it never really gets there. It gets closer and closer and closer, but then it slows down right before it gets there as far as growth goes. So D would be approximately 40 years, or 41 years, 41 and a half years.